2.7 is about z-scores. Now, z-scores give us a way to compare an observation from one distribution to an observation from another distribution. They also allow us to look and just see how unusual an observation might be within a particular distribution. So really, a z-score gives us a measurement about one data value in an entire data set. So why are these useful? What do I need to be able to do with them? All those good questions. So first off, an idea of what we do to calculate them. So the z-score, the formula is right here. It's going to be given to you on the exam. Nothing for you to do here except for know how to plug into it. The formula that I'll give you on the exam will look like this. Z is equal to x minus mu over sigma. So you need to remember that mu is our mean, our population mean, and sigma down here at the bottom is our standard deviation. And what exactly a z-score does is it tells us how far above or below average someone or some value is for its distribution in terms of standard deviations. So you can see here a z-score of 1 means you're one standard deviation larger than the mean. This is very useful when we're comparing two things from different distributions. One example would be like taking the ACT versus the SAT when you're going into college from high school. The ACT is on a scale of 1 to 36, while the SAT is on a scale of 400 to 1600. So in order to compare those two things, we really need to be able to figure out, well, how did you do compared to average? And of course, scale that based on standard deviations, because if our range is 1 to 36, it's a very different range than 400 to 1600. So let's go ahead and see an example we had previously. I'm just going to make one up. So when we talked about, what were we talking about before? Oh, when we're doing the empirical rule, we talked about the weights of adorable fluffy kittens. So let's say we're dealing with a kitten, right? Adorable fluffy kitten. And we know that this kitten weighs, let's say this kitten weighs 2.7 pounds. We know the average weight of adorable fluffy kittens, based on the crap I made up on that 2.5 example, is 3.6 pounds, with a standard deviation of 0.4 pounds. So we could use the z-score formula here. Now this z-score formula, I'm just going to grab it like it was on that previous page. X minus mu all over sigma, right? So the x here represents the actual kitten's weight, our actual observed value. How far is that from this mean? But we want to make sure we're scaling that based on standard deviations, so we'll divide by 0.04. So if we do this math, oh, I had the rabbit open, now it's closed. I don't know what happened to it. Sorry guys, you gotta look through all my crazy ass saved things. I double clicked. What are you doing? I don't know what it's doing. It's not going to open my calculator. This is definitely a calculation worth trying on your own. The reason I say that is I'm still going to try to double click this thing. Why are you doing this to me, huh? Open. You guys can't see me struggling because that rabbit is off screen. I give up. All right. The one thing you want to do when you're entering this in your calculator, make sure that you either use parentheses if you're going to put this on a single line, or you do it in 2 steps. The most common mistake is that students will type it into their calculators like this, and the calculator knows the order of operations, so it'll actually do that division first instead of doing the subtraction first. So either use parentheses or do it in 2 steps. I usually do it in 2 steps. So 2.7 minus 3.6. We are 0.09 pounds below average, and if we divide that by our 0.04, we find out that we are negative 2.25. That's our z-score. What that z-score tells us is that if we drew out what we had done in our empirical rule questions, right? If we started at 3.6 and then did our little bunny hops, 3 above, 3 below, subtracting 0.4, our actual kitten's value here, this 2.7 pounds, is right here, which is 1, 2 1/4 bunny hops away from average. So our kitten here is 2.25 standard deviations below average. And this would be really useful for us if we were going to compare this to say, like, oh, which one is runtier? This kitten, or say we had a puppy, right? I'm not going to try to draw a puppy because that's going to be bad. I have no idea what the average weight of, say, let's make this like a golden retriever puppy. Let's say they weigh more than kittens, obviously. And let's say they also have a larger standard deviation. So we'll call it 0.6 pounds. And let's just say my little puppy, I'm going to draw up my puppy dog. Right? I don't know. That's a dog. Let's say that he is below average, right? Let's go ahead and say he maybe is 3.5 pounds. So obviously he is below average, just like the cat was. He is less than that 4.7 pounds we expected, but is he further below average than the kitten? The only way we could figure this out is by just doing z is equal to and doing the same calculation. So how far is 3.5 below 4.7? But we have a larger spread in terms of puppy weights based on my completely made up numbers, so we'll divide by 0.06. So we do the same thing, 3.5 minus 4.7, negative 1.2, it's a terrible one, all over 0.6, which is negative 2. So this puppy is slightly more normal than the cat because, again, if I was to draw out my cute little empirical rule thing here, 4.7, 4.2, 3.5. Our puppy is right here at 3.5, so he is exactly 2 bunny hops, whereas the cat was 2.25. So he is closer to average, he is more normal, and the kitten is a little runtier in this particular example. So I hope that gives you an idea of what the heck a z-score is. I'll do the 2 examples in a separate video if you want to watch those.